Okay. So before we begin, there is one topic in the book in magnetic systems that is not really correctly described. The results are correct. You see, if you have let's say, an electron in a magnetic field, in the book it says that the energy is given by minus. Okay, there is the mu dot b. And then in the book it says that mu is equal to g times the charge of the object divided by twice its mass times the angular momentum. And then it says that if the object has a magnetic dipole moment only due to its orbital motion, then g is 1. And if there is also the spin contribution, or if the spin contribution is the dominant contribution, then g is 2. And if both of them can contribute to the magnetic moment, then there is this somewhat mysterious looking expression. It has g is equal to 3/2 plus some factors over j times j plus 1, if I'm not wrong. Okay. Now, this is not, strictly speaking, this is not correct. I mean, if you do in quantum mechanics, probably you should see this in 507 in quantum mechanics in the master's program. Now, the magnetic dipole moment does have such an expression, but the full expression is this one, the angular momentum plus twice the spin. So these are, the coefficient of here is 1, the coefficient of S is 2. There are small corrections to these coefficients, 1 and 2. But, and this can be written also as Q over 2m J plus S. The magnetic dipole moment operator is not proportional to J only. But if you look at the averages, or for us what we will be interested in is the energy values at the end of the day when we are calculating the partition function. We are summing over all the energies of the we are summing over the microstates, but the factor that we are summing depends only on the energy of the microstate. And in first order perturbation theory, there is a shift in the energies due to the presence of the magnetic field, which is given by, let's say, alpha state with quantum numbers j and m minus mu dot b, alpha in the alpha state j and m, and this quantity m okay. This is equal to g times q over 2m j. Alpha can be, j and m are the orbital quantum numbers. There's also, they also include the spin. The total angular momentum quantum numbers are there in j and m. Alpha is all the other quantum numbers. This is still correct. So this is the j factor, the g factor. In this sense, the expression in the book is correct, but I mean, it's partial. Now, back to your questions. We will be playing with these three concepts. And one of you, thanks to that person, keeps on asking me what's the difference, why they are important. So what are they? What does distinguishable mean, identical mean, indistinguishable mean? Well, the distinguishable and the other two are easy to separate, kind of. But what's the distinction between identical and indistinguishable? Identical means identical, okay?
I mean, at least I have said that, in the case of indistinguishable, the particles might not be identical, but still you cannot separate them.
If we change the place of these two particles, and for example, entropy does not change, it is indistinguishable. Is the changing of the position, like taking quantities from each other. And if there is a change, if there is no change, it is called indistinguishable. Identical, actually.
Identical means that they crazily enough to be considered as quantization of the same field and the words of Wheeler. There's no difference between them.
That is identical, right?
Identical.
Okay, indistinguishable?
Same thing like you said, if I switch two particles or more, the overall state or wave function of the system would...
But he was saying that that was identical, no?
No, he was saying that
Indistinguishable, so if you just change them, nothing changes.
Can we maybe say that even if they have identical particles, if we can't localize them in space exactly, they are still, if we can localize them, they are distinguishable, even if they are identical.
Any answers? Did you get the question? If
can we really localize any particle without turning into 10,000 problems?
Well, do you have an answer to him? I don't think he means localizing really at this point, but let's say you localize two particles to a region of radius, let's say 1 centimeter, and these two particles are separated by 1 kilometer.
Why not separated by the whole universe?
Okay, fine, no problem.
That's not localization.
No, I think he meant even this much is enough for him, right?
Well, that comes the question, how local is local?
No, we are not discussing local or not. We are mainly interested in this distinguishable or identical particle.
I guess in the book there's an argument like that. If they are localized, they are distinguishable. It doesn't make sense though, I think.
The book probably says that all classical particles are distinguishable, even if they are identical.
Not classical particles.
Yeah.
Photons.
Photons are identical. Photons are indistinguishable.
Yeah, but this is exactly why we have Gibbs paradox in the first place. So the classical motion is faulty. It's not enough.
Okay.
For example, if you have two photons in the system, even if they are identical, you can't distinguish them anymore.
Really?
Maybe.
Maybe.
Or photon or some other particle. But if, let's say, if we have, in such a system, if we have 10 to the 10, maybe, particles of them, we cannot maybe check each of them separately, so they are indistinguishable, maybe.
So you say that
so it's similar, in a similar level.
the critical thing is whether you can track them or not.
In my opinion, yes.
Okay. So why do you think that the classical particles are always distinguishable? Even if they are identical.
Because in physics, we always have this notion of path. So you can always assign a path to each particle and identify the traffic. That's not the case.
Yeah, exactly. You see. Okay, for example, you are all distinguishable people. You are all different from each other. So in that sense, being distinguishable is kind of the more easy to grasp concept. Now, if electrons were classical particles, they would still be distinguishable because classical physics tells us that we can determine the position of the electron given the initial conditions. You can just label each electron by their initial condition. So although they have the same properties, I can determine, classically speaking, which particle came from which initial point. So I can distinguish them by these labels. But quantum physics tells me that I cannot even label them. I don't think even locality would help me. If I have a two-photon system, as your friend pointed out, so let's say if you try to write down the wave function of these two-photon system, you can write it in such a form. So that it should basically be symmetric. For photons, it should be symmetric. So even if, let's say, you measure a photon at the position R1, is it the Psi1 photon or Psi2 photon? You can never tell it. These Psi1 and Psi2 can be localized, or even if you measure, let's say Psi1 is localized here, Psi2 is localized at the other end of the galaxy. So even if you measure a photon over here, you cannot really tell which one it is. Is it the photon described by R1 or R2? So in that sense, photons are indistinguishable. So you see, in this wave function, if you just exchange since it is symmetric, or for fermions, let's say this will be for bosons. We will study bosons and fermions more clearly later on. On the other hand, if they satisfy this one, these are for fermions. So if you change the position of two particles, you don't get a new wave function. You get exactly the same wave function. That is why when you are counting them, these should be counted as one, not as two states, if you exchange the position. And then especially if you go to the limit where more than one particle tries to go to the same state, then this becomes important. For the ideal gas, at least in the limit that we studied, these effects were not important. Because implicitly, we are assuming that the particles making this ideal gas, they are so much separated that they will not, and the probability of having two of them at the same state will be negligible. At the same position and the same state will be negligible, so we just ignore whether they are fermions or bosons. They will not contribute. I mean, the identical indistinguishability property doesn't really contribute. But then we will start calculating the corrections. We will see that if you increase the density or lower the temperature, we will also see that these two basically correspond to the same thing. In that case, bosons will have a lower pressure and the fermions will have a higher pressure than the ideal gas. Fermions and electrons are indistinguishable. Photons are indistinguishable. They are not just identical, they are identical, but furthermore, they are indistinguishable. Two particles can be identical, at least classically speaking, two particles can be identical, they will be distinguishable. Two electrons, if classical physics were correct, two electrons would still be identical, they have the same properties, but still they will be distinguishable. But then, okay, we know that classical physics is wrong, why don't start with quantum statistics? Well, mainly because classical statistics still contains less new concepts. You just add more concepts as you go by.
But still, I mean, if you know it's wrong, I mean, how will we check whether our results still are still correct or not? I mean,
Come on, not you, but in general you are doing PhD. There is no way you will be able to check that your answer is correct or wrong. You have to defend that. If you trust your answer is correct, you have to defend it.
What does the question mean? Does it mean experimentally that we're doing something correct, or?
What do you mean by theoretically being correct?
For example, if you say that, for example, bosones have lower pressure, I mean, if my theoretical calculation means that I have lower pressure, is this what you're asking? How should I know that this is truly correct?
no, I mean, like, for example, there are some like results from the classical physics that we are saying that the result should be this one, but the experimental checking that is wrong. Okay, but
Then we take the classical limit. Then we take the classical, we start with the quantum, then we take the classical limit.
okay, I'm saying that one. I mean, that's the logical one, and we are not doing that, and still using also the classical physics in statistical method.
Any answers to him?
It's simpler, it's faster. That's why you learn ABCs and then you learn literature. We still need it.
Well, you see, at least up to this point, what we have actually learned is that various techniques. We learned method of steepest descent, we learned Stirling's approximation, we learned to deal with huge numbers, and then we also learned things about statistical physics, but even if you leave them aside, you are just learning certain techniques. Classical physics is easy because everything is integration. Quantum physics is sometimes easier because it's summation. So you just learn the technique, and when you need one, sometimes it's easier to solve the classical problem than the quantum mechanical problem. And once you solve the classical problem, you have a very good approximation to the quantum mechanical problem. Even better than just taking the classical limit, by the way. You have all taken analytical physics, right? You have taken classical physics. For example, a very good approximation for quantum mechanical wave function is this one. S being the action, classical action. This is called the sim-classical approximation. So classical physics does give us a good approximation, and sometimes it's just easier to solve a problem in classical physics. Then calculate the quantum mechanical corrections to it. Now sometimes it will be easier to calculate the quantum mechanical problem. Then take the classical limit if you are interested. Yes, other questions? Come on, some of you at least were writing some nice, interesting questions in your report.
When is the Boltzmann energy distribution valid? Under which conditions?
Which one?
Boltzmann energy distribution.
What do you mean, this factor?
Yes, the probability is equal to proportional.
So when is it valid? When can we use this?
I guess we need to have a temperature defined.
Okay, so temperature needs to be defined.
In general, I guess the equilibrium conditions.
The system should be in equilibrium.
But if this system is in equilibrium, can we always define temperature?
Well, that is the one definition of equilibrium, one necessity of equilibrium. When the system equilibrates, the whole system has a temperature. Okay, so when can we use that PR, that probability? How did we drive that probability?
Are you asking for a general case?
I mean, you see, I'm just asking to review what we have done. So you see, his question was, under which conditions can we use this probability expression? So the easiest way to determine what are the conditions to be able to use that probability distribution is to go over the derivation. So what are the assumptions we made while we were driving this relation? And then his answer would be obvious. Once we can identify our assumptions, under any condition that those assumptions are not correct, this probability distribution will probably not be useful for us. Okay, already there was this concept of temperature needs to be defined because that beta is actually the inverse temperature. So without T, we cannot talk about beta. And the system should be in equilibrium because essentially everything we do, it starts with the assumption of an equilibrium system, or at least a quasi-equilibrium system, let's say. And are there any other assumptions we had where we can use this probability?
I think we said that every microstate has the same probability or something like that.
Did we say that?
Did
Every microstate, every microstate. What is this PR? What is this probability, by the way?
The probability of having energy ER.
Do you agree? Is it the probability of having energy ER? What does R stand for over there? Hmm? Okay, somebody else? Macrostate. Okay, the microstate. It doesn't have to be quantum. It can even be classical. So it's the microstate. R represents the microstate. So that ER is the energy of that microstate. So do you still insist that this is the probability of the system having energy ER? Yeah, that is this probability. PR is the probability that the system will be in one microstate. And that probability turns out to depend only on the energy. So if we have more than one state that has the same energy, all of them will have the same probability. But then, well, he made a claim that at some point we said that all the microstates have the same probability. But now we have this probability distribution which says that the probability distribution is not the same for different microstates. And now I will say that you are both correct. Now what is the difference?
There can be many microstates corresponding to this ER.
Okay. But the probability of energy will not be given by this. In that case, we have to multiply this by the density of states or the number of states having the energy ER. So what I am saying is, this is the probability that my system will be in one microstate that has the energy ER. So this probability tells me that the probability of different microstates will be different if they have different energies. Then he says that we also said that all the microstates have the same probability, which seems to contradict this expression. Because this expression tells me that the probability of being in one microstate depends on its energy. It's not the same. And now I will be claiming that both of these statements are correct. How come?
You have to consider the rest of the canonical ensemble in one case. If you consider the canonical ensemble as a microcanonical ensemble, you have to check. Yeah.
The system is always in its most probable state.
So we have to consider only when n is approaching infinity.
Okay, there's this problem of thermodynamic limit. Now, there will be fluctuations which will be negligible, which will go to zero in the thermodynamic limit. So if you have a smaller system, you get larger fluctuations, even in this expression of the probability. But still, back to my question. So he was kind of on the right track. So in the book, you can find these statements in the book, and I will agree with the book. It says that at some point in the book, it says that, okay, the probability of each microstate is the same. In the book still, it says that the probability of being in a microstate is given by this exponential. And then both expressions are correct. So how come? And let me also remind you my previous comment that you have to pay attention to the assumptions you are making in the derivations. Your results will depend on your assumptions.
In that probability, the exponential one, your microstate actually is not unique. Because you are just looking at a small part of the canonical ensemble. For that small part has one microstate, the rest of the canonical ensemble will have many microstates, so it will change the probability. That's why it is not equal to. Why it is not all the energy probabilities are the same.
You see, we had studied the microcanonical ensemble. which is essentially an isolated system. In this microcanonical ensemble, all microstates have equal probability. Well, you can create systems in which this is not correct, but for most practical purposes, this works perfectly. And now we study the canonical ensemble, in which basically our system is in contact with a heat reservoir, so that its temperature is fixed. Well, in this case, the temperature is fixed, so from the reservoir it can just take some heat, give some heat energy to the system, etc. So the energy is not fixed. In this case, then the probability of a microstate will depend on the energy. But you can relate the canonical ensemble to the microcanonical ensemble. Well, basically in two ways. Either you say that, okay, let me treat my system and the heat reservoir, both of them together, as my isolated system. If my whole system is an isolated system, okay, how do we calculate the probabilities? Well, it's the number of outcomes that we want divided by the total number of outcomes. But this time, for a given microstate of my system, there will be many microstates corresponding to the heat reservoir. So the whole system will have many microstates that corresponds to one microstate of the system that I am interested in. So again, looking at the whole system, the probability of each microstate will be the same, but if I only restrict to the microstate of my subsystem, then the probability of the system I am interested in will not be the same. It will depend on the energy. Or basically it's essentially the same thing, but from the ensemble point of view, you can say that, okay, so let's just take many copies of my single system, create the ensemble, and then I can treat my ensemble as my heat reservoir, so that in this ensemble, I can say that each possible distribution of microstates is equally probable, consistent with my constraints. So as I said, these two statements, that probability of a microstate is proportional to e to the power minus beta ER, and that the probability of a microstate is constant, is the same for all microstates, they are both valid, but in different approaches.
Can we consider each snap of a system, which can be microcanonical or canonical, and time evolution of each snap as a mental copies of the actual system? Is it correct for microcanonical and canonical?
Yes, both of them.
And take one system.
Just take many copies.
Sure. And each snap taking a photo, and each snap of this constitute another copies of the system. So this can be
that is one way of constructing the ensemble. And in fact, that construction tells us that ensemble average is the same thing as time average of quantities. And that, just keep in mind that whenever you are measuring a quantity, you are not actually measuring the instantaneous value. You never measure the instantaneous value of any quantity. You just measure a time average of that quantity. You can make this time average versus this time over which you are averaging to be very small, but still it's a time average. Now the fluctuations most of the time will be so small, the time in time at least, the fluctuation will be so small you won't be able to measure them. You see, if you consider the pressure, what creates the pressure in these walls? The collision of the atoms with the wall. Well, they are discrete, they just collide one by one. So the pressure acting on a wall will be fluctuating. But your equipment will not be enough to measure that fluctuation. You are not just also averaging over time, you are also averaging over position. You can never make a measurement at a mathematical point. You just measure an area. You can make that area very small, but still it will be large. So you are just averaging over that area. And both of these averages, both averages over space and averages over time, doesn't allow you to measure the fluctuations. Unless, of course, you can increase the fluctuations by essentially not taking the thermodynamic limit. If you lower your number of particles, you will be increasing the fluctuation. Then you can measure it. And if you have sufficiently precise equipment, you will measure what's called the thermal noise. Yes.
And the Hamiltonian was limited in the upper end. But there we were considering dipoles, right? And these dipoles were localized. So we're not actually considering the whole Hamiltonian in that sense. So can we separate the Hamiltonian into parts and calculate the temperature for each of these parts? And then maybe the sum of those temperatures would correspond to the actual temperature calculated from the total Hamiltonian.
Yes, any suggestions?
In the last section there was we had a system of dipoles, and they were localized, and the Hamiltonian was limited in the upper end, so we were able to get negative temperatures. But in reality, I think we don't have any negative temperatures, right? It's limited with 0. It should be. So what I'm asking is this: if we have a Hamiltonian that is the sum of several terms, can we just ignore all but one of those and calculate the temperature if the Hamiltonian is that? So H equals H1, and we calculate some temperature, call that T1, and then there's actually other terms, H2, H3, and do the same thing for those terms. Okay, so yes, a little more German. And can we write this?
Okay, so what he's saying is we have the Hamiltonian, which we can write as the sum of various terms.
Yes.
Then, if I understand it correctly, he said that maybe we can assign some temperature T1 over here, another temperature T2 over here, another temperature T3 over here. And can we identify the temperature of the whole system as the sum of these?
Maybe some other way around.
Let me put a question mark here. So this is the question. Because essentially, I mean, what in negative temperature, what is done is you only treat the dipoles, localized dipoles, and claim that they have negative temperature.
We just choose some terms in the Hamiltonian
Mhm.
system.
Any ideas?
I don't know, I have a question regarding this when it comes to intensive and extensive property. Usually temperature should not be extensive, so if I expanded my system, it's okay to some energies, but this here means that T also should be extensive, which is not.
Summing the temperature, as your friend pointed out, doesn't really make too much sense because T is intensive. It's not the sum of the temperatures at various parts. But still, the other part of the question still stands.
Some other function may be appropriate.
Yeah, how can we separate a part of the system, not even a part of the system, just one property of the system, and assign a temperature to it? That's what we do in negative temperatures.
If we trace this temperature back to temperature in the equation we found the negative temperature, I think it goes until the first law, right? The first appearance of the temperature and when we derive that.
The zeroth law is which tells us that there is this concept of temperature. The first law is actually this one. This is the first law.
In the derivation of that equation, we found that there is a negative temperature. If you trace back, I think it
Goes to the second law.
Second law, and it goes to the first law, the TDS.
That is the second law.
Yeah, second law, but TDS we defined it as DQ, and then we wrote that. Is S from dq over T.
Okay.
Then we have a much different S right now. We don't have dq or T in the Boltzmann's entropy formula. We derived the canonical ensembles equations and we found the negative temperature from there. And those equations were a combination of the first law and the Boltzmann entropy law. So this is not an answer, but I'm making questions stronger. So it's second here. We started from dq over T, and now we are in position of alignment.
You see that negative, you see dq over T, you are right. Well, negative temperature basically tells you that if you give heat to the system, the entropy drops. So that is what negative temperature tells us. And that is actually what we are seeing in this graph also. If you keep increasing the energy of the system, the entropy drops. If there is a maximum energy of the system, of course. Now let me ask you one question. Your friend was saying that in his question, You cannot go below 0. So how come you have negative temperatures? So let me ask you this question. Are negative temperatures colder than T equal to 0? Or they are hotter than any positive temperature system?
We already answered that.
Hmm?
We already answered that. If hotter and cooler means direction of flow of heat, then negative T's are hotter than infinite.
Yeah.
Temperature. We answered
So
that.
negative temperatures are not actually below T equal to 0 in the sense of energy. They are above T is equal to infinity. So here this is T is equal to plus infinity. And at this point you have T is equal to minus infinity. You get negative temperatures when you keep heating the system even after it has an infinite temperature.
Could you repeat the concept explicitly? I didn't catch it.
This last one.
Yes.
You see, negative temperatures, you can obtain negative temperatures by adding heat to our system. And what we would normally expect is if you give heat to the system, the temperature increases. It gets hotter and hotter. But for these special systems, so we still are not answering your question, but for these special systems, what happens is if you keep adding heat to the system, the temperature first reaches T is equal to infinite. And then if you keep heating it, the temperature goes to minus infinity. So essentially, negative temperatures have more energy than positive temperatures. So in that sense, negative temperatures are not below T is equal to 0. They are above T is equal to infinity. So if you have any system with positive temperature, if you bring it in contact with a system with a negative temperature, you always have transfer flow of heat from negative temperatures to positive temperatures. And if you have a system that cannot have negative temperatures, these two systems will never come to equilibrium. Well, okay, let me rephrase it. They will eventually come to equilibrium, but the equilibrium will always be at positive temperatures. Now, that is a problem in measuring these negative temperatures because the thermometers we use to measure the temperature, they don't have negative temperatures. So if you use just ordinary thermometer, and I mean, how does the thermometer work? You just mark some scales in the ideal gas thermometer, for example, you put some scales, and then you just measure the height of the gas column or the liquid column, depending on how you build your thermometer. You bring it in contact with the system whose temperature you want to measure. And when both systems come to equilibrium, you read the temperature. But an ideal gas thermometer cannot be used to measure negative temperatures because an ideal gas temperature will never come in equilibrium with a negative temperature system because ideal gas does not support negative temperatures. Even all the other methods of measuring the temperature, like you can use the resistivity to measure temperature. Well, resistors also do not support negative temperatures, so you cannot use a resistive thermometer to measure negative temperatures. So you have to come up with some other tricks to determine the negative temperature. Now, back to his question. How come, I mean, you see, in the experiment done, we just consider the magnetic properties of the nuclei to discuss these negative temperatures. But the nuclei, the dynamics of the nuclei, okay, is given by there is the external electrostatic forces between various nuclei, there is the kinetic motion, etc. And once you have kinetic motion, there is no upper limit of the energy. And hence, once you take into account the kinetic motion, there can never be negative temperatures. So are we justified to pick up just some degrees of freedom and study that system?
At low temperatures or?
You see, negative temperatures are not low temperatures.
No,
Okay.
In the assumption where we can just treat the dipoles, can we just consider low temperature system or high strength magnetic field systems?
Okay, a good question.
Then the kinetic energy contribution will be much lower than the dipole energy.
Are you convinced?
Then the upper limit will be very high. So it would be very hard to go to negative temperatures.
No, I mean, we don't go to negative temperatures like this. We go to negative temperatures like that. You see, in the experiment that is mentioned in the book, they don't obtain negative temperature by just giving heat to the system. That's not how they create a negative temperature system.
The universal magnetic field. So the system cools down on its own.
You see, what cools down? Yes, it loses energy, but slowly. Okay, let me give an answer. At least give my answer, let's say. And then we might go for a break. For example, if I would say that let's just pick up 20 molecules over here, treat it as my subsystem, would you have any question in that? Any problem? I can always take these 10 particles over here and then treat it statistically. I can either do, if I don't allow, if I prevent particle exchange, I can use the canonical ensemble. Well, if I allow the particle exchange also, then I can also use the grand canonical ensemble. We will study the grand canonical ensemble, but you are saying that if I just pick up 20 molecules in this room at this corner, let's say, you have no problem in dividing my system into such a subsystem. Now, what we are actually doing from the formal perspective, from the mathematical perspective, H is equal to pi squared over 2mi. I might have different particles plus some potential term. And most of the time we ignore that potential term. So when I'm picking these 10, 20 particles over here, I'm essentially picking some degrees of freedom. Just in this case, if we are in 3 dimensions, if I actually pick 10 particles, then I'm just picking 30 degrees of freedom. But in analytical physics, for example, you have probably seen that degrees of freedom, they are more or less all the same. You can talk about the momentum or the position, you have the generalized momenta, generalized coordinates. You can just separate the degrees of freedom and still, formally at least, you can do the same thing. Now, of course, here, an important step is this one, ignoring the potential. I don't have to ignore all the potential, but if I want to separate my system, I somehow need to separate, make sure that the potential and the interaction between the subsystem I choose and the rest of my system should be small. Because otherwise, we are quite often treating different subsystems of my system as more or less statistically independent. That's one assumption we are doing quite often. Well, if you choose your subsystem itself to be macroscopic, that's usually not a big deal because most of the interactions happens on the surface of your subsystems when the two subsystems are in contact with each other. That is where most of the interactions comes into the game. But for large macroscopic systems, the degrees of freedom on the surface, they are negligible compared to the degrees of freedom in the volume. So that won't be such a bad approximation. Well, let's see what is done in the book. We have the Hamiltonian. There is the there are some terms which describe the dipoles of the nucleus interacting with the external magnetic field. There are terms describing the rest of the degrees of freedom of my system. Well, let me not use let me just say nuclear dipole. Plus there is the nuclear dipole and rest interactions. Now, what do these interactions do is they just cause the flow of heat. Just like in the case of dividing my system into a subsystem over here and the rest, the interactions on the surface, they cause the heat to flow back and forth. The same thing over here. That third term, the nuclear dipole and the rest interactions, that is the term responsible for the flow of heat and for the thermalization of my system. But nuclear dipoles, they interact very weakly with the rest of the system. You see, there won't be a flow of energy, a strong flow of energy from the energy stored in the dipoles to the kinetic energy. So to an approximation, I can ignore this. But if I ignore them, then my system is divided into two. Two subsystems which are not interacting. Of course, I mean, I'm ignoring those terms. If I ignore them, they are completely not interacting. So if they are not interacting, well, I can treat the thermodynamics of each part separately. You see, I can have one choke over here, another choke over here. These two chokes are not interacting with each other. I can just do the thermodynamic treatment of each one separately. They can have different temperatures, etc. Well, basically the idea over here. But of course, those additional terms, those terms that I ignored, they are actually there. Then the question is, what is the thermalization time? You see, there is a heat flow, but heat flow takes time. If heat flow, I mean, if I just do back to this choke example, these two chokes, there is a heat flow between these two chokes because the gas in between carries heat. They radiate. But that heat flow is very slow. To a very good approximation, I can just heat this to 1000 degrees, cool this down to minus 20 degrees Celsius, and both of them will be in equilibrium. I can do the equilibrium thermodynamics of each one of them separately, assuming I don't wait, I don't know, 1000 years. For short periods of time, I can just treat them as independent. Well, the same thing over here. Those ignored terms, the interaction of the nuclear dipoles with the rest of the degrees of freedom, they cause an equilibration between dipole degrees of freedom and the rest, like the kinetic energy. But the equilibration time is like 5 minutes in the experiment, at least. It takes 5 minutes for the whole system to all of the degrees of freedom to equilibrate. So if I make some measurements within, let's say, a few seconds, well, I can treat the nuclear dipoles, degrees of freedom corresponding to the nuclear dipoles, to be independent of the degrees of freedom corresponding to the rest of the system, the remaining degrees of freedom. So if I study my system for just a couple of seconds, my nuclear dipoles will be an independent thermodynamic system with its own temperature. And that temperature can be negative. But the whole system, as I said, if you study the system in a time scale of, I don't know, 10 minutes, the whole system is not in equilibrium. But if I study the whole system for, I don't know, a couple of seconds only, or let's say 1 minute even, I can treat each one of these sets of degrees of freedom to be in equilibrium on its own with its own temperature. Okay, before you go for a break, let me just give you a couple of non-curricular information. You see, these are essentially the memory types that is used nowadays. Now, immediate memory is something that you use right away and forget right away. Like when somebody is giving you a phone number, you just dial the phone number, but once you have dialed the phone number, you just don't remember the number. That is what's called the immediate memory. Working memory is what allows you, if you just have looked through the material just coming before the class, and then that information is in your working memory, you remember that material during the class, you might, at least, or when you are studying for your exam, you just review it the week before the exam. So what you are actually doing is you are just transferring that information to your working memory. But the problem with the working memory is it doesn't last long. It just, typically it lasts 24 hours, but it can last for a couple of weeks. That is what the research tells. So the idea is how can we get this information to the long-term memory? Long-term memory is what you remember even in the long run. So how do you measure the long-term memory? Well, by doing pop exams, doing quizzes, exams without any earlier preparation, which the students object, and even the regulations do not allow us to do. We cannot do midterms unannounced. We have to announce them at least 1 week before. But the problem with that approach is when we announce them at least 1 week before, you prepare for the exam, so everything goes in your working memory, you come to the exam and you answer the questions correctly, then you forget them. And that is probably not what you want, because that way you have to review them before every exam, and eventually there is the qualification exams, you have to review them again once more to put all of them in the working memory. But the problem with at least the qualification exams is there are so many materials that you don't have enough time to put everything in your working memory. So even if you are successful in the course, quite a number of students fail in the qualification exams. So that is the idea of why we are doing all this. So it should come, we should be, and that should be the purpose. When I lecture, when you are following, you are essentially putting everything in your working memory. Well, it's in your memory. When you ask yourself whether you have understood it, your answer would be yes, because you remember them. But the question is, do you remember them the day after? Well, that's why I think it's important that you study the material before coming to the class. That's why you have the pre-reports. At least you put that information, if you read it at least, if you read the material at least once, I'm not asking you to review everything, just read it once. So that will at least put some of them in the working memory. So we emphasize it again. That's another reason why I'm insisting on you asking questions, because that way you will be more active, you will be reviewing everything that you remember. I'm expecting you to ask questions and answer them. So you constantly, during the lecture, review the material that you have remembered to come up with the answer, hoping that it eventually goes to the long-term memory. And I also advise you to review the material the day after, so before 24 hours. Okay, let's give a 10-minute break.
Hocam şimdi şeyin olduğunu anlamadım. Herkesin kendi temperature'ı var ama merak ediyorlarsa ortak bir temperature'a dönüşüyor.
You see, if there are interactions between the system, what do you mean by interactions, by the way? Usually what we mean when we talk about interaction is, do the systems exchange energy? If the systems exchange energy, eventually the system will come to equilibrium. What do we mean by equilibrium? Nothing will change in the long run. So the system will, in the statistical terms, the system will always, not always, but let's say in the thermodynamic method it will be always, the system just does what is more probable for it to do. And the more probable thing is to increase the entropy. So the entropy of the whole system will increase. And eventually it will come when this equilibrium is reached, the system is basically in its most probable state. And that most probable state satisfies this equation. Throughout the system, meaning that take any subsystem of your whole system, calculate its entropy, the derivative of the entropy of that subsystem with respect to its energy will be constant. And that constant is what we call the temperature. So in equilibrium, when all the heat flow is over in the macroscopic sense, not in the microscopic sense, when all the heat flow ends, the temperature is uniform. And since there's always the kinetic energy which doesn't have an upper bound, in this sense you cannot have negative temperatures. But then, you see here, one key concept that we use is the equilibrium is when heat flow stops. But then I can ask you this question, to what accuracy? If the heat flow is very slow, at a given instant for a very short amount of time, I can ignore it to a first approximation. If I ignore it, then each part which exchange heat but in a very slow rate, then each part can itself be in equilibrium, independent equilibrium. This is also sometimes called quasi-equilibrium. The whole system is not actually in equilibrium, but with the precision we have, with the precision we seek, let's say, within that precision, each part separately is in equilibrium. Now, if you apply this principle to the dipoles, nuclear dipoles, you do get negative temperatures. The negative temperature of the dipole, not the whole system. But then you can object, well, how can we say that, does it make sense to ignore that heat flow? There will always be heat flow in that case. But you see, if you look at from that perspective, there is not, if you want to say that equilibrium is, there shouldn't be any heat flow, even approximately, in that case, there is no system in equilibrium. There is a constant heat flow everywhere in the universe. But still, if you are satisfied with a given precision, then we can talk about thermodynamic systems. And practically, that's always the case. For example, this room is in equilibrium. Within, let's say, 1 hour, I can treat this room as a system in thermal equilibrium. Well, okay, let's ignore the students. Why? I know that the pressure is the constant throughout the system, the temperature is the constant throughout the system. So it's in equilibrium. But if I study the classroom, including you, well, it's not in equilibrium. You are 37 degrees Celsius. The temperature of this classroom should be something around 25 degrees. Definitely the whole classroom with you inside is not in equilibrium. Well, even if we just go out now in the break, there will be a uniform temperature in the classroom, let's say. But even in the long term, let's say if we study the system in 1 day, again, it won't be in equilibrium. Now it's 25 degrees. At night, it probably drops down to 10, 15 degrees. So there's the concept of equilibrium itself always comes with a time scale. Within a given time scale, some systems can be considered in equilibrium. In fact, for every system there is this time scale. Within that time scale, the system can be in equilibrium. Well, there are various time scales, by the way. There's also the equilibration time scale. Beyond that time scale, you see, in this classroom, the time scale will probably, within 1 hour, I can treat the system as equilibrium. Within 24 hours, if I observe this classroom for 24 hours, it's no longer equilibrium. Yeah, the same thing with these dipoles. If you study those dipoles within, let's say, up to 1 minute, in that case, the equilibration time was 5 minutes. If you study the nuclear dipoles in 1 minute, you can identify its temperature. But in 10 minutes, no, it doesn't have any temperature. Or the temperature will always be positive, let's say.
Is there a difference between thermalization and equilibration for the systems we are studying here?
Well, there are a couple of concepts that are also used interchangeably. There is the concept of thermal equilibrium. Okay, your friends wants to go for a break. Okay, let's continue after the break. Ya bir konuşalım diye. Sana cevap olarak mail yazmaya üşendim de.
Hangi şey mi? MATLAB şey mi hocam? Ben size...
Deney. Lablarla ilgili.
Onu ben atmadım, Şahin attı.
Şahin mi? Ha, pardon.
Beni hep Şahin'le karıştırıyorlardı.
Pardon hocam.
Onu Şahin attı hocam.
Tamam. Olur.
Sistemin toplamında bir iyi total var.
Tamam.
Şimdi ben bu iyi total'ı bu her bir parçaca işte bir şekilde dağıtabilirim. İşte onu E1 verebilirim, buna E2 verebilirim ama böyle ki bu enerjilerin hepsinin toplamı E olacak şekilde. Şimdi ben bu enerjileri parçacıklara nasıl dağıttım? Yani bir tane dağılım verirsem bu benim bir tane macro state'im oluyor değil mi?
Macro state'in E total. Macro state'ini belirleyelim.
Yani o zaman bunu değiştirdikçe aslında
Macro state'lerin değişiyor.
Ama tamam da o zaman mesela ben bu parçaya şimdi kuantum mekaniksel olarak bakarak ben bu parçacığın belli bir enerjisi, E1 enerjisi olduğunu biliyorsam bu E1 enerjiyi sağlayacak farklı kuantum number'lar da var.
Yok, şimdi zaten o yüzden enerjiyi dağıtırım demiyorsun sadece. Diyorsun ki bu enerjiyi kullanarak şu parçacığı şu state'e koydum.
Aslında bunu siliyorum aslında
bunun state'ini söylüyorum, quantum number'larını söylüyorum.
Söyleyerek onun toplam işte enerjiyle
evet.
Söylüyorum. Anladın da biz bir normalde bir sistem varsa yani bu sistemin işte şu kadar enerjisi var diyebilme şansımız oluyor genellikle. Yani o zaman aslında biz sistemi
macro state'ini biliyorum.
Direkt olarak biliyoruz.
Macro state'ini, micro state'ini değil.
Peki, ben daha şey düşünmüştüm. O zaman macro state'in enerjisi dediğimiz şey de bu oluyor direkt.
Hocam şurada working memory'den long term memory bahsettiniz yani. O 24 saat mi geçmesi gerekiyor?
Ya tam nasıl çalıştığı bilinmiyor şu anda. Ama dedikleri şey şu, okuduğum kadarıyla working memory ortalama genelde 24 saat sonra working memory'deki bir şey long term memory'ye geçmediyse unutuluyor.
Peki geçiş nasıl oluyor? Yani sürekli bir review yapmak mı? Ya da aynı şeyle karşılaşma mı?
Yani tekrar onu sağlayan şeylerden biri. En azından şunu yapmış oluyorsun sürekli tekrar ettiğin zaman. Yani long term memory'ye geçmediyse working memory'de tutmaya devam ediyorsun geçene kadar.
O direnci kırıyor
Yani dedikleri bir şeyin working memory'den long term memory'ye geçmesi için iki şeye ihtiyaç var. Diyor ki one, it should make sense and it should have a meaning. Yani bir anlamı olacak, bir de sana bir şey ifade edecek. Mesela eğitimde nedir bu?
İkisinin arasındaki fark ne?
Şöyle diyeyim, saçma sapan denklemler yazabilirim tahtaya. Onun bir sensi yoktur. Şimdi öyle bir şeyin long term memory'e geçmesi zor.
O zaman ilk başta iyi anlamamız.
Anlaman gerekiyor. İkincisi sana bir şey ifade etmesi lazım. Yani mesela senin yaptığın araştırmayla ilişkisini kurabilirsin. Ya da işte derslerde genelde ne yapıyoruz? Ha, bunu öğrenmezsen sınavdan düşük not alırsın diyoruz. Mesela o da bir meaning olabilir ama çok da büyük bir meaning değil o. Yani mesela yani kendi araştırmanda ilişkilendirebiliyorsan, kendi hayatınla ilişkilendirebiliyorsan, öyle bir meaning katabiliyorsan o zaman long term memory'e daha çok çabuk geçiyor. Diyorlar. Sen de deneyimliyorsundur eminim ki yani. Araştırmanla ilgili şeyleri daha çok hatırlıyorsundur. Orada hem sürekli tekrar ediyorsun. Sana bir şey it makes sense. Sürekli tekrar ediyorsun. Aktif olarak katılıyorsun. Yani pasif olarak oturup dinlemiyorsun. Derslerde çoğunlukla yaptığımız ne? İşte hoca geliyor anlatıyor. Sen de pasif olarak dinliyorsun. Sonra working memory'ye geçtiği için anladım diyorsun. Ama sonra bakıyorsun yok.
Hocam şimdi oda sıcaklığına demir alsak, sıcaklığını bir termometreyle ölçsek, bir de spinlerden ölçsek, bağımsız bir şekilde, spin miktarları, magnetization'dan, bunlar aynı sıcaklığı mı verecek?
Evet. Ama demiri ısıttın. O ocağın üzerine koydun, demir ısınmaya başladı. 5 dakika içerisinde ölçersen, ilk 1-2 dakika sonra ölçersen, demir daha sıcak olacak, nükleer dipolları daha soğuk olacak. Henüz thermalize olmadı çünkü ikisi.
Ya o şeyde o, yani elektronların o, yani ferromanyetik özelliği veren kısımlarından ölçülen şeyler aynı oluyor. Ya ben mesela Curie temperature'ı hesaplasam, hiç demirin şeyini hesaba katmadan, taneciklerin hareketini hesaba katmadan, Curie temperature'ı sadece manyetik interaction üzerinden hesaplasam, o bana gerçekten ideal gas temperature veriyor.
Okay, there is one thing you should pay attention to. Magnetization that you measure is created by the electrons, not the nuclei.
Yok, ben elektronlarla. I mean electrons.
Okay, electrons interact strongly with the remaining degrees of freedom.
Yes,
So the thermalization time with the dipoles of the electron and the other degrees of freedom will be very short.
yes.
In a very short amount of time they will thermalize. So if you measure the temperature using the spin of the electrons, or if you measure the temperature using some other means, you will get the same, more or less the same temperature. Why do I say more or less? Well, I mean, I'm sure you can come up with at least a hypothetical setup in which you give heat to the system in a very short amount of time and measure the temperature right away, before the dipoles and the atomic motion thermalize. Except, I mean, if you ignore the cases that you tailor in a special way, the temperature of the electrons and the temperature of the atomic motion will be the same. They will be in equilibrium. But nuclear dipoles, they might not be in equilibrium because thermalization time for the nuclear dipoles is long, like 5 minutes, at least in the setup that is described in the book. Ha, tamam. Can you close the door? Okay, so quite often we have all these different kinds of equilibrium. There's a thermal equilibrium, mechanical equilibrium, thermodynamical equilibrium. Well, thermal equilibrium basically means that I can define a temperature of the system. Which basically means that there is no flow of heat in the system. Mechanical equilibrium is when system has a pressure. Well, the system has a pressure when, there is no flow of particles, there is no changes in the volume, etc. Thermodynamic equilibrium just means both of them. So, for example, I can come up with a system which can exchange energy there is a barrier over here, there is a P1, there is P2 over here. I can allow heat exchange. If I allow heat exchange, eventually they will come to the same temperature. Now, if you remove the barrier, at that moment, for a very short amount of time, you can talk, the temperature of the system is still the same. It's in thermal equilibrium. But the pressure will not be same. You cannot define a uniform pressure for the system. There will be flow of particles from left to right until the pressure is equilibrated, so the whole system will have a definite pressure. That is when the system reaches mechanical equilibrium. And the system was already in thermal equilibrium. Now it will be in mechanical equilibrium, so the system is in thermodynamical equilibrium. Both the dynamics have equilibrated and the thermal properties have equilibrated. Okay, back to your questions.
In the paramagnetism chapter, the writer calculated the partition function in a classical way, but that partition function was not exactly the sum over states, but it was an integral over the angles. So there has to be a constant times that partition function should be the real partition function which will give us the free energy. But it continued that way. So is there a problem? When you are calculating the entropy, the logarithmic, natural logarithm, you cancel that constant. I can see that. And also when you consider the probabilities, multiplying the partition function and the other integral above with some constant, they will cancel out. But if you want to try to find the free energy from that partition function, I think you should give the wrong answer.
Do you understand the question or comment? Your friends didn't understand you. Okay, so let me give it answer like this. In fact, I will be connecting it to your answer also, to your question. Now, what is the partition function? Okay, let's repeat it again. You will be answering this question, I don't know, hundreds of times during this semester. What is the partition function? Sum over e to power minus beta ER. Sum over all microstates. Let's do the classical treatment for simplicity. What is the energy of the system? for a classical system. Let's try to identify several degrees of freedom also. Well, let me write it in this form. There is a center of mass degrees of freedom. Well, most of the time we just go to a reference frame in which this is 0. There is the translational motion of the atoms. Particles making the system. Let me just call this ETR. And this translational motion will basically depend on the momenta, if you choose your momenta suitably. Then there is the, let's say, vibration. If you have molecules, now there is the interaction. Between particles. Let me just call this E int. This quite often it will be a function of the positions only. And well, this, let's just ignore it. Plus, if these particles are molecules, or let's say if these particles are dipoles, or, okay, molecules, there will be internal motion and internal potential energies. Let's say that the degrees of freedom, let's just label them capital Pi and capital Qi. These are the internal degrees of freedom. Plus, there might be some external fields, and they can be in dipoles, the energy due to the magnetic dipoles. And this will be a function of, let's say, di, the dipole of each field, and of course the external field. I'm not writing the external field explicitly. And depending on your system, you can just divide these degrees of freedom into more refined pieces, if you like. You can add more terms, but the idea is you have these generalized coordinates, and the total energy of the system will, most of the time, will be just the sum of these generalized coordinates. And assuming that all these degrees of freedom are in equilibrium, then we know that we have to assign them the same temperature to all these degrees of freedom. Now, the partition function for this system will be, well, I'm summing over, there will be a sum over the integral over Pi and Qi due to the translational motion of these particles. There will be an integral over capital Pi and capital Qi. This will be due to the internal motion and internal potential energy. A sum over, let me just use ddi, this notation. Di will not be my degree of freedom, but whatever the degree of freedom you use to describe that dipole, in the book it uses the angle, the solid angle. The orientation of the dipole can only change, its magnitude doesn't change. That's the approach the book has. And then you have the exponent of minus beta ETR plus E int plus E internal. Internal int is the interaction between the particles, internal is the internal energy, plus E magnetic dipoles. But now you see all of these four terms, each one of these four terms, they depend on different coordinates and different momenta. And I'm just integrating over all these different coordinates and momenta to calculate the partition function. But since there are no mixed terms, well, you might end up having mixed terms. In that case, you cannot do this. But if there are no mixed terms, if you choose your coordinates and momenta suitably, the number of mixed terms will be small. It will be reduced. And in certain cases, you can even ignore those terms. In that approximation, I can separate this as dpi of e to power minus beta. This is due to the translational motion of the particles making my system. And then I have dqi e to power minus beta e int. These are due to the interaction of the different particles making my system. And then I have integral over the internal coordinates of e to power minus beta e internal. And then I have the integral over the I of e to power minus beta e magnetic dipoles. And so the partition function itself actually separates. There is the translational motion, the partition function corresponding to the translational motion, the partition function corresponding to the interactions between the particles, the partition function corresponding to the internal degrees of freedom, and the partition function corresponding to the magnetic dipole. Well, if you calculate the free energy, the free energy will be minus kT times logarithm of Qn. So the free energy can be separated. In the book it says A. There is the free energy due to the translational motion, free energy to the interactions. There is a contribution to the internal degrees of freedom, and there is a contribution to the magnetic dipoles. Now the question is, what are you interested in? If you are interested in to obtain the free energy of the whole system, this is what you should calculate. But let's say in the book, at least what we are interested in, at least in the example in the book, we are interested in the magnetization of the system. Well, how do we define the magnetization? This is essentially the derivative of the free energy with respect to the external magnetic field. But you see, only these magnetic dipoles . Yes, there's a minus. Only that term depends on the magnetic field. So if you are interested in the magnetization, you don't need to calculate all free energy.
Actually, what I mean was in the dq and dq integral, for instance, you should divide that integral with omega 0, which was h to the power 3n.
Oh, okay.
But you didn't do so in the other cases. In the, for example, dipole case, you are not restricting the position.
Sure. Well, you see, there was this question in classical statistics. We are counting the number of microstates, so each point corresponds to one microstate, and in a given region, there is an infinite many number of points. And then what we had done was, okay, so every point doesn't really correspond to a microstate, but in phase space there is a certain volume which corresponds to a given microstate. Classically, there is no reason for this to be so, but quantum mechanics kind of tells us why there is this finite volume, because mainly you can relate it to the uncertainty principle. But as your friend points out, that is ignored. Well, it doesn't really make any difference if you are interested in calculating the magnetization, because that unit volume in phase space just gives a constant in the free energy. If you just change that volume, you are just changing that constant. If you are interested in a constant in this, that depends on n. It depends on the number of particles, because the number of particles changes the dimension of your phase space, and that volume element depends on the dimension of your phase space. But if you are not interested in the chemical potential, in all the derivatives you are interested in, that constant will just drop. You don't need to take it into account. And even when you are interested in the chemical potential, well, that constant will not be important most of the time, at least.
If you want to find the A magnetic dipole, then you should consider the quantum case, right?
Well, at least in that quantum case, you can identify what that volume element is. In fact, that would be a nice homework. Do you understand the homework? Yes, you can calculate this partition function using classical physics, classical dipoles. And then the integral will be over the orientations of the dipoles. There, just like in the earlier cases, we have to insert some volume which corresponds to one microstate. A priori, from classical physics, we don't know it. But we can choose that volume, that unit volume, such that the classical partition function, at least in certain limit, is equal to the quantum mechanical partition function. So what should be that volume?
This is for a dipole, right?
For the dipole problem.
So there are phi and theta, so it's 2 in dimension, phase space.
Okay, yes. Let me ask you this question. Can it be H? Why and why not? You see, in the book, it just converts the sum over the theta, because if you have a dipole, its magnitude is fixed. The microstate is determined by the direction in which the dipole points. But the directions are described by the solid angle. So you are actually summing over all the solid angle that the dipole can point to. And the solid angle is this one, sine theta, d theta, d phi, divided by, there should be some omega 0. At least that is what your friend claims. Now the homework question is, what is this omega 0? My question is it possible, at least in this case, just take one dipole, is it possible to have omega 0 to be H? You say, this is the problem. I don't know the answer. But what I know is the partition function calculated in quantum mechanical case and the classical case should give the same result in the classical limit. That's what I know. But I can say you that omega 0 cannot be H. I will be surprised even if it contains H. Why? You see, we have dp dq. Here, let me put a prime. Omega 0 prime should have the dimension of pq, which is the dimension of h. Well, here omega 0 should have the dimension of theta phi, which is just 1. It doesn't have any unit. If you put h, you see, essentially we are just counting the number. It should be just a dimensionless constant. dp dq over omega 0, it should be dimensionless if it is counting the number of states. So if you put h over here, you should put something else with a dimension, which should cancel that dimension. But just looking at the properties of the phase space itself, I don't see any other dimension-full quantity. At most, I expect it to contain some factors of pi. At most. Mu? What is mu? You see, phase space is a construct that is determined by your degrees of freedom, not by your Hamiltonian. If in the Hamiltonian, if I put H is equal to 0, B is equal, magnetic field to equal to 0, there is no mu over there. Of course, you should also think, does this question make sense? Is this an integral over phase space?
In the Day2 case, we had a restriction, but in that case, we don't have a...
Okay, let's go step by step. Is that integral an integral over phase space? Because the volume we identify in phase space. It's just a physical space. There's no momenta over there. It's not phase space integral. So even talking about omega 0 in that space doesn't really make too much sense. What should be the corresponding phase space integral? You should add the corresponding momenta. And this should probably be h squared. Okay, homework will be more or less this, but not in this form. Now there's I think it was a problem at the end of chapter 2. Okay, that will be your homework. You see here, there is also no sine theta.
If we make a canonical transformation and we can get the Jacobian determinant, so we can get the scaling factor, so it's very important. Approach the problem that way.
Okay, what is p theta, p phi? Anyway, it will be your homework. Don't worry. I will write it down explicitly. I just copy from the book. Yes, any last questions?
In the page 71, the author talks about thermal vegetation. Like it described as like the
magnetic field tries to align the dipoles in one direction, and the magnetic thermal agitation tries to randomize its direction.
Yes, but I can understand what's the reason for this. I mean, it just says this, but I don't like there's no argument for why it should be.
Okay, try this experiment. Take your hand, try to rotate it, and then go and hit the wall. So in which direction your hand will be rotating right after you hit the wall? Huh? Okay, you will be just hit the wall. I mean, I don't know in which direction you will bend afterwards, so your rotation direction will be different. You see? Okay, in the dipole example, I mean, in most of the examples, we ignore the interactions. But that's actually an important part of thermalization. Thermalization needs interactions, and otherwise there's no change in the energy distribution, kinetic velocity distribution, etc. Thermalization doesn't happen without interactions. Now just imagine these electrons or whatever they has, these dipoles. They are moving around and they are colliding. When they are after the collision, their orientation need not remain the same. So if you have these two electrons, they are constantly vibrating, colliding with each other. Colliding doesn't need to be with touch. I mean, they're colliding also, scattering off each other electromagnetically. So these scatterings, they can be, the idea of these statistics is, to start with, we assume that the interactions are so complicated that they almost appear random. So when they are colliding, after these collisions, their orientations will change. They will not stay in the same orientation. You have these two electrons, when they collide, their orientation will be rotated due to collision. Okay, so this is the thermal agitation. Because you all have this idea of temperature. The temperature is the average kinetic energy, which is actually, due to the virial theorem, the average kinetic energy is proportional to the temperature, whatever the system is. Now, if the temperature is higher, that means the kinetic energy of the particles making the system are higher, and they will be colliding more fiercely. If they are colliding more fiercely, it's more probable for the orientation of the magnetic dipoles to change. So that is the agitation. If they collide so often, you see, you have this effect of the magnetic field. What the magnetic field will do is it will try to align the magnetic dipole with the magnetic field. But keep in mind, energy is conserved. If you just take this dipole, this isolated dipole, and put it in a magnetic field, it will not align. It will just, even classically, it will just make a flip-flop motion, or it will rotate around the magnetic field. It will never align. You need changes, energy flow for alignment. So on one hand, you have the magnetic field, there are these interactions. Magnetic field will try to align if there is energy flow to the other degrees of freedom or to the environment. That is one effect. The other effect is there is the thermal motion of these things. And during their thermal motion, they will be colliding with each other. And these collisions will just try to change the alignment, because in these collisions, you can transfer energy. And if you just, let's say, if there's a dipole pointing in this direction, if you transfer energy to it, well, it will not be in its ground state, but in the excited state. Of course, some of that transferred energy will go to the kinetic motion. Some of it will go to the orientation of the dipole. And how much goes to which one is determined by the interaction between the kinetic energy and the dipole degrees of freedom. Well, you can also think of it like this. You are here sitting in your chairs and trying to listen to me. Just imagine there are, 20 kids around, moving around, just shouting and hitting, colliding with you, etc. You will not be sitting so orderly. So that is the thermal agitation. They have a large temperature. And you see, in the class, you are trying to be aligned in that direction. With the kids, you never know. Okay, see you next Monday.